Polyurethane grouting is a versatile solution for construction challenges. It works by injecting material to fill voids and stabilize soil. This provides waterproofing and strengthened structures. It's ideal for tunnels and dams like this. In this video, we will learn what is PU grouting and how it's different from conventional methods. Polyurethane is expanding resin to seal cracks, providing a watchful silhouette. Unlike conventional methods, Geoframes and cause less disruption.
Welcome to today's Explainer. Today, we're diving straight into some truly fascinating, completely invisible engineering that literally keeps our modern world standing. I mean, we walk right over it, we drive through it, we live inside it, but we hardly ever think about the unseen forces fighting a constant battle against nature, right beneath our feet. Seriously, have you ever wondered what actually stops the entire ocean from crushing an underwater tunnel? Or, say, what prevents groundwater from slowly, quietly sinking a massive residential building? Well, the answer lies in a vital geotechnical risk management tool. It's a highly specialized process called grouting, and it tackles this universal, age-old problem of structural degradation and water ingress, especially when it comes to tunnels and complex underground works. So let's jump right in and explore how modern materials science is literally holding our infrastructure together. Okay, here is our roadmap for today. 1. The basics of grouting. 2. Conventional methods. 3. The PU revolution. 4. Pros and cons. 5. Method of selection. And finally, 6. Our conclusion. Let's start with Section 1, the foundation, basics, and conventional methods. Now, historically, when an underground tunnel sprang a leak or the soil shifted, engineers turned to a familiar cast of conventional players. The most common, standard Portland cement, which is still often used for massive civil projects, like those giant earthen dams. Then we have chemical grouts, like sodium silicates or acrylamide. Acrylamide is actually fascinating because it boasts an estimated lifespan of over 300 years, mostly used in sewer pipeline systems. There are also incredibly rigid epoxy resins and bituminous grouting. But, how do all these actually differ physically? So, the absolutely crucial point here is the physical difference between these two main families of grout. Cement grouts are what we call suspended solids. They actually contain tiny solid particulates, meaning their ability to penetrate soil relies entirely on how finely the cement was ground up at the factory. On the flip side, we have chemical grouts. These are true solutions. They have virtually no suspended solids, giving them highly effective microscopic penetrability. Basically, they act exactly like fluid water right up until they cure, which is incredibly useful for deep underground works. Moving on to Section 2, the PU revolution, chemistry and mechanics.
Okay, so polyurethane, or PU grout, represents a fundamental shift in civil engineering. We're moving away from traditional cementitious binders to high-performance polymer matrices. Chemically speaking, polyurethane is formed through a highly exothermic polyaddition reaction between isocyanates and polyols. I know that sounds super technical, but what that means in plain English is that a violent heat-producing chemical reaction turns a liquid resin into a highly resilient, water-blocking polymer foam literally right before your eyes.
And the working mechanism here is just incredibly elegant. Think of this sort of like biological white blood cells rushing to heal a wound. First, the liquid PU is injected directly into a concrete crack or the loose soil around a tunnel. Second, it reacts with the moisture that's already present there. Third, it violently expands, actually using carbon dioxide gas generated during the reaction as a blowing agent. And finally, it perfectly seals the void, automatically adapting to every single microscopic crack and crevice. Now, this brilliant mechanism is divided into two main categories you'll actually encounter out in the field. The most fundamental decision in waterproofing is choosing between hydrophobic, meaning water-fearing resins, and hydrophilic, or water-loving resins. Hydrophobic PU only needs a tiny trace of moisture, just about 3%, to activate. It repels water permanently, it won't shrink in wet-dry cycles, and it's absolutely your go-to for massive dynamic leaks. Hydrophilic PU, on the other hand, actually incorporates water into its own structure. It expands less but cures into this highly flexible gel that's perfect for environments that stay constantly wet. All right, Section 3, the trade-offs, pros and cons of PU grouting. Let's look at some of the major advantages here. Polyurethane offers incredible flexibility to resist cracking and dynamic movement, whereas traditional cement is, well, notoriously brittle. Also, take a look at the UV stability. By utilizing specific aliphatic resins, polyurethane won't yellow when it's exposed to the sun. Epoxy grouts, by contrast, are notorious for turning a really nasty yellow under UV light. This makes PU just as perfect for your sun-drenched bathroom tiles as it is for stabilizing a deep underground mine. 15 to 30 minutes. That is the staggering cure time for polyurethane to achieve structural strength. Just compare that to the painstaking 24 to 28 days required for traditional cement grout to reach its full strength. I mean, if you need an active, gushing leak stopped immediately in an underground tunnel, PU is simply unmatched. It's a total game changer. And here is another incredible metric for you. 20. A hydrophobic PU foam can expand up to 20 times its original liquid volume. Because it expands under its own pressure, it aggressively hunts down and completely fills irregular, complex void geometries that static, non-expanding cement simply cannot reach without leaving dangerous air pockets behind. However, to be completely impartial, we do need to look at the limitations and disadvantages of PU. It is vastly more expensive upfront, coming in at roughly $60 to $80 per uncured gallon. Furthermore, its success relies heavily on the engineer's precise matching of the chemical interaction to the environment. If it's applied incorrectly, or while it is actively curing over those first 72 hours, tests show there can be a temporary release of organic carbon materials into the surrounding water, so it definitely requires extreme precision to use effectively and responsibly. Which brings us to Section 4, Method of Selection, Key Decision Factors. So, when evaluating geologic effectiveness, grain size is basically the holy grail for geotechnical engineers. Notice how standard cement is completely restricted to coarse gravels and sands? That's because of the suspended solid particulates we talked about earlier. But as you move down the chart into the fine sands and coarse silts, polyurethane and other chemical solutions are essentially the only materials capable of actually penetrating and stabilizing those really tight geologic formations. Ultimately, the method of selection on a chaotic job site relies on this specific matrix of factors. What exactly is the soil composition? Is there an active, high-pressure leak in the tunnel right now? Can we afford to wait 28 days, or do we desperately need this fixed in 15 minutes? And crucially, do we need a lightweight fill? Think about it. If you were trying to lift a sunken concrete slab, pumping tons of heavy cement under it might just make the whole thing sink faster. In that specific scenario, a feather-like, highly expansive PU is your indisputable champion. And finally, Section 5, Conclusion, Carrying the Weight of the World. This powerful quote from our source material really perfectly summarizes the gravity of the situation. Hidden underground, grouting helps to guarantee the safety of countless mines and civil structures, and most importantly, the safety of billions of people. Whether it's a massive dam holding back millions of gallons of water, or the deep foundation of the very building you're sitting in right now, grouting is quite literally the structural risk management that keeps our society functioning safely. And that leaves us with a pretty fascinating question. As our cities grow denser, our tunnels dig deeper, and our engineering challenges grow more and more extreme, will traditional cement eventually become a relic of the past, fully replaced by these smart, flexible, expanding chemical polymers? The next time you drive through a dry tunnel deep underwater, ask yourself, is it heavy concrete holding everything up? Or is it a feather-light, completely invisible, expanding polymer keeping the ocean at bay? Thanks so much for joining me on this explainer, and remember to keep looking beneath the surface.
Welcome to the Polyurethane Grouting Guide. For underground structures, the step-by-step methodology involves injecting grout into crack. However, limitations exist in tunnels with high water flow or deep voids. Plan carefully to avoid risks and ensure success.
Welcome back, experts, to today's explainer. Look, if you're out there managing heavy industrial facilities, infrastructure, or deep underground tunnels, you already know that water ingress and structural settlement aren't just minor inconveniences, right? They are critical, drop-everything-and-fix-it emergencies. So today we're going to explore a highly technical, totally actionable guide for using polyurethane or PU grouting to resolve those severe structural and load-bearing failures. We are completely moving past those old-school traditional cement-based fixes today. Instead, we're looking at a highly tunable, rapid-curing polymer matrix that is literally revolutionizing civil engineering and geotechnical stabilization. I mean, just think about the immense, staggering cost of facility downtime. We're talking about taking a traditional 28-day cement curing process and replacing it with a 15 to 30-minute structural polymer solution. And get this, it boasts an estimated lifespan of 75 years. It's an absolute game changer.
Okay, let's just quickly run through today's roadmap. We're going to cover diagnosing failures, polymer chemistry, hydrophilic versus hydrophobic systems, single versus plural systems, optimal resin density, and we'll wrap it all up with equipment and safety.
All right, let's jump right into Section 1, diagnosing structural and drainage failures.
Now, before we even think about injecting a single drop of anything, we have to rigorously map the symptoms.
You're going from visual sinkholes all the way down to minute pressure gradient shifts. Say you're looking at a tunnel floor slab or maybe a massive embankment dam. Those very first signs of drainage failure might just be a localized sinkhole or a little surface slumping, but you've got to look deeper. Are you seeing downstream turbidity? Meaning, does that leakage water actually contain eroded soil material? Because if it does, that is a massive red flag indicating internal erosion or piping. From there, you've got to escalate to quantitative monitoring. You'll use piezometers to really track those shifts in the pressure gradients and water levels deep inside the structure. And finally, you confirm the exact location and the full extent of the structural void or cracking through core drilling or even ground-penetrating radar. You have to know exactly what you're dealing with.
A quick but absolutely crucial precaution here. When you're dealing with weak or loose mountain rocks or really sensitive foundation interfaces, you have to exercise extreme caution. You must avoid high-pressure overpressurization. Why? Because that could inadvertently cause further fracturing of the rock or even deform the structure itself. Remember, our goal is to stabilize and seal the area, not to blast the existing cracks even wider apart. So this means you're strictly controlling that injection pressure and you're selecting a material with a highly predictable expansion rate.
Moving on to Section 2, the chemistry of polyurethane grouting. Like I said earlier, this isn't your traditional cement. This is a highly tunable material science solution. Polyurethane grouting achieves its structural strength in a fraction of the time it takes standard cementitious binders to cure. And here's the best part. Unlike cement grout, which can actually shrink over time and leave you with new gaps, expanding polyurethane naturally seeks out and completely fills those irregular voids. It's incredibly smart material.
So what's actually happening under the hood? The core performance of this grout is dictated by reacting an isocyanate group with a hydroxyl group, which is typically a polyol. Now, in heavy industrial settings, we're usually using aromatic isocyanates, like methylene diphenyl diisocyanate, or MDI for short. When you combine that MDI with lower molecular weight polyols, boom, you create this rigid, high-strength, closed-cell foam that is just perfect for lifting heavy concrete slabs. On the flip side, if you swap in high molecular weight polyols, you create a flexible, elastomeric polyurethane. And that flexibility is absolutely vital when you're injecting into dynamic cracks where you're expecting thermal expansion or heavy, continuous machine vibration.
Now this right here, this chemical equation, is exactly why PU is so unbelievably effective against active water ingress. The reaction literally uses the leaking water to its own advantage. When the isocyanate hits that water, it reacts to form an amine and carbon dioxide gas. And that CO2, it acts as a blowing agent. It causes the resin to rapidly expand and forcefully fill the void, creating this watertight pore structure that completely stops gushing, high-pressure water leaks dead in their tracks. It's brilliant.
Okay, Section 3, hydrophilic versus hydrophobic systems. Let's break this down.
You absolutely must choose carefully here based on your specific environment. Hydrophilic grouts are typically single-component systems. Now, hydrophilic means they literally love water. They require a continuously moist environment even after curing, otherwise they might shrink. They'll expand about 4 to 6 times their original volume, forming a flexible gel or foam, which makes them excellent for continuous active leaks. On the other hand, hydrophobic grouts, the water haters, require very little water, only about 4% to react. Because of this, they easily withstand dynamic wet to dry cyclic environments without shrinking at all. Plus, they can aggressively expand up to 20 times their original volume.
Let's keep moving. Section 4, single versus plural component systems. Consider this table your ultimate field cheat sheet. Keep this in mind. Single component grouts have very low viscosity, meaning they flow really easily. You'll inject them into loose sandy soils or subterranean concrete pipe cracks, and they simply react with the existing groundwater already down there. Plural component systems, however, are for the heavy lifting. Literally, you use these to fill massive voids and for slab jacking to completely re-level sunken concrete. But because they require mixing 2 separate chemicals exactly at the point of injection, they rely on specialized proportioning equipment. This equipment actually heats the chemicals and pushes them through a series of hoses to a strict 1-to-1 ratio impingement gun.
Section 5, selecting optimal resin density.
When you factor in the expansion component, the cost efficiency of polyurethane becomes honestly staggering. Get this, some emergency PU resins, the ones specifically designed to halt catastrophic water inflow, have a foaming expansion capacity of up to 3,000%. Yeah, 3,000. That means a tiny amount of liquid resin transforms into a massive void-filling structural plug almost instantly.
But matching the density to the load is absolutely vital here. For those plural component systems used in slab jacking, the density ranges from 2 pounds per cubic foot all the way up to 12 PCF. To put that in perspective, a high-density 12 PCF rigid foam can exert approximately 10 psi of lifting pressure as it expands. That is enough controlled force to effortlessly lift an entire sunken industrial warehouse floor back to perfect grade without any excavation whatsoever. Pretty amazing, right? Conversely, you would select low-density, flexible elastomeric foams if you're sealing cracks around vibrating heavy machinery. If you used rigid foam there, it would just shatter from the vibration.
Finally, Section 6, Equipment Setup and Safety Protocols. Let's talk about the physical execution. When looking at the hardware, you'll see specialized dual-tank injection pump systems. These are required to push the chemicals under incredibly precise pressure. Notice the completely separated tanks. That is crucial. By utilizing independent heated hose lines for the polyol and the isocyanate, the components are kept strictly 100% separated until they finally meet in the mixing chamber of the injection gun. This is what prevents those premature, catastrophic exothermic reactions right inside your expensive equipment. During the measuring and mixing phase, whether you're using a massive heated proportioner or just drill mixing smaller batches on site, your execution here must be flawless. Ratios must be exact. If they aren't, the chemical reaction won't trigger correctly, you won't achieve the proper gel time, and you definitely won't reach full compressive strength. Now, for the actual on-site administration. The maintenance team first drills insertion holes directly into the structural failure, like an active crack in a concrete wall. They install packers tightly into those holes, attach the pressure hoses, and then actively force the expanding polymer deep into the hidden void. The second that liquid hits any moisture inside the wall, it expands, actively chasing the water out and permanently sealing the pathway. It's really something to see in action. But remember, and I can't stress this enough, these are highly reactive exothermic materials. They expand rapidly and they can generate significant heat. Therefore, full personal protective equipment is an absolute mandate. It is not a suggestion. Your team must be equipped with hard hats, high-visibility vests, safety goggles, and heavy-duty chemical-resistant gloves at all times when handling, mixing, or injecting any of these polyurethane resins. Safety first, always.
So, let's bring it all together and think about the immense cost of facility downtime. If a tunnel floods or a warehouse floor collapses under heavy forklift traffic, time is your absolute most expensive variable. Ask yourself right now if your maintenance strategy is truly up to date with modern material science. Are you really still waiting weeks for cement to cure, or are you ready to deploy a permanent, highly tunable polymer solution that cures in literally minutes? The technology is here, guys. The choice is yours. Thanks for joining me on this explainer, and I'll catch you in the next one.
Thank you for watching this video. If you enjoyed it, please give it a thumbs up. And don't forget to subscribe to the channel. Thanks for your support.